Let's say you've been dreaming of jumping into a black hole your whole life. You're haunted by one burning question: what's in there? You've devoured every book by Stephen Hawking and Kip Thorne, watched every film and documentary. You know that at the center of our Milky Way galaxy lies a supermassive black hole called Sagittarius A star. And now your chance has come. You're healthy enough, the ship is ready, and you set off to meet the unknown. You arrive at a safe distance from the black hole. Then you leave the ship and begin your free fall toward it. Your fall will last about an hour, and it ends in death. The spaceship stays in orbit, watching your descent. But before the fall even begins, you face your first problem: gravity. The black hole's mass is millions of times greater than the sun's. Its gravitational pull is so strong it captures stars and gas, forming a glowing, whirling disk of hot plasma. This accretion disk spins at nearly the speed of light. Friction within the disk causes violent turbulence and heats the matter to billions of degrees. As a result, it emits intense radiation: ultraviolet, X-rays, and even gamma rays. Blacks smell at rays and friction and often can leave ultraviolet, X-rays, and even gamma rays unshielded. You'd be instantly blinded or burned alive. To survive this journey, let's imagine you're wearing an ultra-advanced spacesuit. It can withstand the extreme heat and filter out deadly radiation. Even so, the disk is so blindingly bright that your helmet comes equipped with a high-tech visor that dims the glare and sharpens the view. You notice the disk glows blue. That's because your visor filters only the visible spectrum, and high-energy blue light dominates, just like with the hottest stars. Interestingly, one side of the disk looks brighter than the other. This is due to the Doppler effect. Just like a car passing by changes pitch, the side of the disk moving toward you compresses light waves, making the light more intense. The side moving away stretches the light, making it dimmer. You also notice the far side of the disk appears distorted, curved around the black hole. That's the gravitational lensing effect. Light bends as it passes the intense gravity near the event horizon, making you see objects behind the black hole. The stars in the background look slightly blue too. That's because time passes slower for you than for those distant stars, another Doppler effect caused by gravity. You and your stars cause the gravity effect. Caused by gravity, light from them appears sped up and blue shifted. Falling through the disk feels bizarre. During the first 10 minutes, the black hole appears to recede, even though you're accelerating toward it. This optical illusion is caused by relativistic aberration. You're seeing light from a distorted angle. 10 minutes in, you're moving at 4% the speed of light. The black hole now looms larger in your view. As you continue to fall, your speed increases. Light in front of you brightens, while light behind dims. Again, Doppler effect. Soon, the disk of matter slides below you. Then, after 57 minutes, it vanishes. You've reached the innermost stable orbit. Beyond this point, matter spirals into the black hole. Gravity here is so extreme that things accelerate inward uncontrollably. In just 2 minutes, you've fallen twice as close to the black hole as before. Now light itself can no longer escape. You've reached the photon sphere, where light orbits the black hole. Just 24 seconds later, you cross the event horizon. There's no going back. Strangely, you still see the spaceship orbiting above, the stars behind it, even your own body below. Despite falling inward, the black hole doesn't swallow your entire field of vision. It occupies only about 15% of it. Why? Again, aberration. Because you're now traveling so fast. Light from all directions appears to come from ahead. Your field of vision compresses forward. Behind you, everything looks wider, distorted. The spaceship looks bigger now, even as you leave it behind. The next 30 seconds pass in a blur. You start to regret not choosing a bigger black hole. Larger ones give you more time. Suddenly, a terrifying force grips your body. This is spaghettification. You will literally be turned into spaghetti. Spaghettification will reach such a degree that even the atoms of your body will be torn apart and eventually disintegrate. Your feet are slightly closer to the center than your head, and that tiny difference means you're being stretched and crushed simultaneously. You feel like you're falling onto a flat, pitch-black floor. A glowing ring surrounds you, the last light from the outside world. Then, in the blink of an eye, your remains collapse into the core. The matter of your body stretches and compresses until space and time themselves twist and collapse beyond recognition. This is the end of your journey. What happens next? We don't know. Modern physics fails here. Our theories predict a singularity, a point where space-time bends infinitely, but no one knows what that really means. As Nobel laureate Roger Penrose once said, the biggest mystery is singularities, because we don't know what to do with them. You see, black holes hide singularities from us. When matter collapses toward the center, its density grows more and more, exceeding anything imaginable, and we have no idea how to describe the physics happening at the center, because the densities, temperatures, and God knows what else are beyond all limits. Roger Penrose uttered these words after receiving the Nobel Prize. He openly admits that science has no theory to describe the conditions inside a singularity. Black holes are not as black as we once thought. They're not the eternal prisons they were once imagined to be. In fact, things can escape a black hole, outward and possibly into another universe. More and more physicists now believe that black holes are not cosmic prisons, but rather powerful tools, perhaps the most powerful telescope in the universe, or even a quantum computer beyond anything we can build. Many now see them as the key to unlocking the true structure of reality. They say truth is stranger than fiction, and nowhere is that more accurate than with black holes. These cosmic objects are more bizarre than anything science fiction writers have ever dreamed up. But they're not fantasy. They're real. They're science. Black holes offer physicists a natural laboratory for the most extreme experiments imaginable. Inside them, space and time are so distorted that by studying their effects, we uncover strange and sometimes unsettling truths about the universe itself. So let's use black holes as a kind of magnifying glass. Through them, we'll explore how time and space can literally switch places, whether black holes are gateways to other universes, why space might not be fundamental at all, where the infinite number of universes might be hiding, and how you can be burned and spaghettified at the same time. By the end of the video, you'll have a mental map of the most extreme objects in the universe, and you'll understand why some physicists now say, in our quest for a quantum theory of gravity, black holes may offer a glimpse of a deeper layer of reality. This video is based on the book Black Holes, The Key to Understanding the Universe by physicists Brian Cox and Jeff Forshaw, a work that brings together Einstein's theories, cutting-edge quantum mechanics, and the latest thinking in cosmology. Brian Cox is often called a punk physicist. Before becoming a professor at the University of Manchester, he played keyboard in the band D-Ream. Today, he's a Royal Professor for the Public Understanding of Science and a Fellow of the Royal Society. His co-author, Jeff Forshaw, is an expert in quantum chromodynamics, a professor at Manchester, a winner of the Maxwell Medal, and a marathon runner. He jokes that after 30 kilometers, his thoughts on particle physics become especially clear. In many ways, their personalities reflect the book itself, energetic, curious, and deeply grounded in the science. Now, let's begin with a monster. At the center of our galaxy lies Sagittarius A star, a supermassive black hole weighing 4 million times more than our Sun. It warps space-time so severely that not even light can escape. Black holes form when the universe's largest stars collapse. They live at the hearts of galaxies and on the edge of our understanding. When a huge amount of matter is squeezed into a very small space, gravity does something extraordinary. It creates a black hole. Our physical laws can predict them, but they cannot fully explain them. Every black hole is a puzzle, a cosmic mystery we haven't yet solved. It all began with Einstein. His general theory of relativity predicted two very strange things. Massive stars will inevitably collapse into black holes, forming singularities, points of infinite density. There's also a singularity in our past, the Big Bang, the moment the universe and time itself began. In other words, Einstein's theory of gravity also tells us something profound about the nature of time. But for a long time, even physicists didn't believe black holes were real. Einstein himself argued in 1939 that black holes do not exist in reality. His colleague Arthur Eddington put it more bluntly: there must be a law of nature that prevents a star from acting so absurdly. But there isn't. And stars do, in fact, behave exactly that absurdly. Today, we understand that black holes are a natural and inevitable part of the life cycle of very large stars, stars more massive than our Sun. And since there are millions of such stars in our galaxy alone, there are also millions of black holes. Stars are enormous balls of matter fighting against their own gravity. They burn hydrogen, turning it into helium, and in doing so, they generate the pressure that keeps them from collapsing. Our Sun fuses about 600 million tons of hydrogen every second. That's like consuming a mountain of fuel every second for billions of years. The Sun might seem massive, you could fit 1 million Earths inside it, but in the grand scheme of things, the Sun is actually a dwarf. The largest stars are over 1,000 times bigger. Some span 1 billion kilometers in diameter. Put one in the middle of our solar system and it would engulf Jupiter. And these giant stars are doomed. Once they burn through their fuel, gravity wins. They collapse. Small stars become white dwarfs, objects the size of Earth, but with the mass of the Sun. Quantum mechanics saves them. Electrons cannot remain stationary. When they are compressed, they begin to move frantically. This creates pressure. In 1930, a 19-year-old student named Subramanian Chandrasekhar, sailing on a ship to England, did the math that would shake astrophysics. He realized something no one had dared to calculate before. Electrons cannot move faster than light. So, if a star is more than 1.4 times the mass of the Sun, electron pressure won't be enough to stop it from collapsing under its own weight. When that happens, something extraordinary forms: a neutron star. Inside, protons and electrons are crushed together to form neutrons, resulting in a sphere the size of a city, yet heavier than the Sun. A teaspoon of this material would weigh 1 billion tons. Some neutron stars spin up to 700 times per second. The first one was discovered in 1967. It pulsed so regularly that astronomers initially thought it might be a signal from aliens, and named it LGM-1, short for Little Green Men 1. Gravity on the surface of a neutron star is 100 billion times stronger than Earth's. Anything that falls onto it is instantly crushed into a particle soup. But even neutron stars have their limits. If a collapsing star has more than 3 solar masses, not even neutron pressure can save it. The collapse continues, and the star becomes a black hole. Today, we can detect them. In 2015, the LIGO observatory detected gravitational waves from the merger of 2 black holes 1 billion light-years away. One was 25 times, the other 36 times the mass of the Sun. They collided in a mere 0.2 of a second, releasing more energy than all the stars in the observable universe combined. In 2019, the Event Horizon Telescope gave us the first image of a black hole. In the M87 galaxy, 55 million light-years away, it is 6.5 billion times the mass of the Sun. The dark center is its shadow, where light can't escape. The glowing ring around it is superheated gas, spiraling into the abyss. Black holes are the ultimate testing ground for physics. To understand them, you need all of it: thermodynamics, quantum mechanics, and, of course, Einstein's theory of relativity. Let's start there. In school, gravity is usually described as a force, the thing that keeps you from jumping too high. In 1687, Isaac Newton described it mathematically, and his equations still work well for predicting things like spacecraft orbits. But Newton made 2 major assumptions. Time is universal. If you sync all the clocks in the universe, they'll always tick in unison. Space is absolute, a fixed, unchanging backdrop for everything that happens. It sounds like common sense, but both assumptions are wrong. In 1971, physicists Joseph Hafey and Richard Keating conducted a brilliant experiment. They bought plane tickets and took 4 atomic clocks on flights around the world, first eastward, then westward. When they returned, they compared their clocks with identical ones left on the ground. The result? The clocks on the eastbound flight were 59 nanoseconds behind, and those on the westbound flight were 273 nanoseconds ahead. Exactly what Einstein's theory predicted. Time isn't fixed. It flows differently depending on your speed and your position in a gravitational field. So what about space? Surely that's solid? Let's put it this way. Look at your hand. Would you believe that the distance between your fingers could depend on who's looking? Einstein believed it, and experiments confirm it. Take the Large Hadron Collider at CERN, the world's largest particle accelerator. Its circumference is 27 kilometers from our point of view, but for the protons inside, moving at near light speed, the circumference shrinks to just 4 meters. Einstein understood this as early as 1905, years before any such experiments. What led him to this conclusion? It came from a contradiction he saw between Newton's theory of gravity and Maxwell's theory of electromagnetism. Maxwell's equations say that light always travels at the same speed, no matter how fast the observer is moving, about 300 million meters per second. To understand how strange this is, imagine you're an astronaut on a spaceship. You throw a ball forward. From your perspective, it moves at the speed you threw it, but to someone watching from Earth, the ball's speed is the throw plus the speed of the spaceship. But with light, that's not the case. If you shine a flashlight forward inside the moving ship, both you and the observer on Earth will measure the speed of the light as exactly the same. Not added, not subtracted. This is weird. So there were only 2 ways to explain this: change Maxwell's equations or change our concepts of space and time. Einstein chose the second. If Einstein could be credited with pulling one idea out of thin air that led directly to his most famous equation, E = mc squared, it would be the concept of the space-time interval. The idea is beautifully simple. Imagine our astronaut again standing in the spaceship with 2 flashlights, one pointing forward, one backward. He turns them on at the same time. Since the ship is at rest from his point of view, the light beams reach the front and rear ends simultaneously. But now imagine the same scenario from Earth. Because the spaceship is moving forward, the light traveling toward the rear of the ship has a shorter distance to go and reaches the wall first. The beam heading forward has a longer journey since the ship is moving in the same direction. So from Earth's perspective, the events are not simultaneous. How can we resolve this paradox? We have to abandon our usual concept of time. In this scenario, the rear of the spaceship is slightly in the future relative to the middle, and the front is slightly in the past. As strange as it sounds, this isn't speculation, it's measurable. There's one quantity that all observers, regardless of their frame of reference, will agree on. If they calculate time squared minus distance squared, they will all get the same result. This quantity is called the space-time interval, and it is invariant, meaning it doesn't change based on the observer's perspective. That's a big deal. Invariants are fundamental because nature doesn't care about our point of view. So, if we want to describe nature truthfully, we must speak in the language of invariance. When we discover an invariant, we uncover something objective about the universe, something deeper than opinions, coordinates, or reference frames. That's why dozens of physicists, including Nobel Prize winners, call the equation for the interval one of the greatest equations in all of physics, maybe even in all of science, because it's not just clever math. It's a glimpse into how the universe is really built. And the word fundamental matters. It means this is how reality works. We don't know a deeper explanation. The interval is a kind of distance, but not just distance in space. It's the distance in space-time between 2 events. What's an event? It's something that happens somewhere and sometime. For example, snapping your fingers, it happens here and now at a specific point in both space and time. Relativity is all about the relationships between events, how far apart they are, whether they can interact, and whether one can cause the other. This way of thinking is surprisingly intuitive. We naturally say things like, "Let's meet tomorrow night at the pub." That's an event in space-time. Now think about the events of your life. Your first day at school, New Year's Eve with your grandmother, that one unforgettable night at the pub. Line them up, one after another, like beads on a string, and you get your world line, your unique path through space-time. All the moments of your life, past and future, exist somewhere in space-time. Your memories, they're still there. Your future, including your death, is already part of that line. If you had a perfect stopwatch, one that you started at birth and carried with you always, it would measure the length of your world line, from the moment you were born until now. And that length is what we call your age. Wouldn't it be wonderful if you could move freely along this line? Jump back to your childhood, or forward to the distant future, but the interval won't let you, and here's why. Imagine you light a candle. Its light spreads out in all directions, forming a three-dimensional bubble of photons, expanding at the speed of light. Now take a two-dimensional slice of that bubble. It becomes a circle, expanding outward with time. If you stitch together all the snapshots of that light bubble, frame by frame, you get a shape called a light cone, expanding from a single point in the past into the future. The sides of this cone are always tilted at a 45 degrees angle, because the speed of light is constant. In 1 year, light travels exactly 1 light year, no more, no less. Now, here's the crucial insight. No matter what path you take through space-time, you will always remain inside this cone. You cannot escape it. Let's say a supernova explodes in a distant galaxy. That event can't affect us until its light cone reaches Earth. No information, no signal, not even gravity, can get here faster than light. We'll only see the explosion when we enter its cone. This is how causality works. One event can only affect another if they are connected by a light cone. No light, no influence. No cone, no contact. But the most important thing light cones reveal is the difference between space and time. What's the real difference? In space, we have freedom. We can move in any direction, turn around, retrace our steps, or even move in loops. In time, there's no such freedom. All objects, including you, are forced to move in a single direction, from the past into the future. It is impossible to turn back in time. Light cones clearly show this difference. In space, we are free to choose any direction, but in time, successive light cones force us to move exclusively forward. We cannot turn back because we remain trapped inside these cones. This property allows us to strictly define the concept of time. In Einstein's theory of relativity, time is defined as the direction in which light cones point. It's the one direction you can't turn around in. Time is the path all physically possible trajectories follow, the route our future must inevitably take. Space, by contrast, is composed of all the directions perpendicular to time. In a region of the universe where there's no gravity, completely empty space, space-time is flat. Here, space and time form a perfect symmetrical grid. Light cones are evenly aligned, and the speed of light is the same in all directions. In this kind of idealized environment, time can be defined globally. On a diagram, it would run from left to right in a clean, orderly fashion. Light cones are a key element of the special theory of relativity, which describes the universe without gravity. The general theory of relativity adds a key idea. Space-time has a geometry that can be curved. Matter and energy curve space-time in their vicinity. Objects do not move under the influence of gravity. There is no force in Einstein's picture. Gravity is pure geometry. To grasp this idea, imagine a two-dimensional world. The residents are flat beings, let's call them flat earthers, who live on a surface with no concept of up or down. They crawl forward and back, left and right, but never upward. Their eyes are flat, their world is flat. To them, reality is two-dimensional. Now imagine a rebellious thinker among them, the legendary physicist Flat Albert, who dares to suggest the unthinkable. There is another dimension, a direction we cannot see. Suppose he's right. In truth, the flat earthers live on the surface of a table, and the third dimension, up, is very real, though they can't perceive it. They encounter strange obstacles, a coffee cup, a lamp, a book, all objects rising out of their world. They can't pass through these regions and are forced to go around them. So how does Flat Albert deduce the existence of an invisible third dimension? He observes something peculiar. Light and shadow. I've figured it out, he says. Those shifting dark patches are shadows, two-dimensional projections of objects in three dimensions. Albert uses mathematics to prove that the shadows they see are just traces of higher dimensional objects. Now, here's where it gets profound. In our world, the space-time interval, that thing which doesn't change no matter who's observing, lives in four dimensions. What we think of as distances in space and differences in time, they're just shadows. They change depending on your point of view. We too are like Flat Albert. We can't picture a four-dimensional object, just as he couldn't picture a coffee cup. But that doesn't stop us from using logic, math, and imagination to explore it. Flat earthers might assume their table is perfectly flat, but with precise instruments, they'd discover strange effects. Triangles whose angles don't add up to exactly 180 degrees. Parallel lines that eventually converge or diverge. This is what physicists mean when they talk about the curvature of space. General relativity tells us that matter and energy warp space-time. This curvature explains what we experience as gravity. And don't worry, even professional physicists can't visualize four-dimensional space-time. When it comes to this, we're all Flat Alberts, staring at shadows. Fortunately, there's a beautiful way to make sense of it. Penrose diagrams, elegant visual tools that track how light cones behave in curved space-time. General relativity is often called one of the most beautiful theories in science, not because the math is easy, it's famously hard. There's a well-known story when Arthur Eddington was told he was one of just 3 people in the world who truly understood Einstein's theory. He paused for a moment and replied, "I'm trying to remember who the third is." The beauty lies in the ideas, in the fact that gravity isn't a force, it's geometry. As physicist John Archibald Wheeler once put it, space-time tells matter how to move, matter tells space-time how to curve. The hardest part of general relativity isn't understanding the concepts, it's calculating the curvature of space-time. Black holes are one of the rare cases where this can be done with precision, but there's a problem. How do you draw something as mind-bending as curved four-dimensional space-time on a flat surface, like a chalkboard, a page, or a screen? This is the same dilemma cartographers face when trying to represent a spherical Earth on a flat map. Back in 1569, the Mercator projection offered a clever solution for sailors. It preserved angles. You could draw a straight line between 2 points and the angle would give you your compass heading, vital for navigation. But the trade-off was distortion. On a Mercator map, Greenland looks as big as Africa, even though Africa is 14 times larger. At the poles, the distortion becomes infinite. They can't even be shown. Now enter Roger Penrose, a brilliant mathematician with the soul of an artist. Imagine your canvas is space-time, and your brush is gravity. That's how Penrose thought. He set out to do the impossible, to depict infinity itself. The full history of the universe on a single sheet of paper, and he did. Penrose came up with a trick. What if we could compress infinity without distorting the path of light? Using a special mathematical transformation, he squeezed infinitely distant regions into a finite diagram while preserving the angles of light rays, the key to preserving causality. The result was the Penrose diagram. In the simplest case, flat space-time, it looks like a rhombus, a diamond. The entire universe from beginning to end fits inside this finite diamond. Yes, there's distortion, enormous distortion, but it's carefully chosen. Like the Mercator map, the Penrose diagram is a conformal projection. It preserves angles, especially the 45-degree lines that represent light rays. No matter where you are on the diagram, light cones remain vertical. This makes it easy to visualize cause and effect across vast stretches of space-time. Now let's use this idea to understand how gravity curves light cones. Start with something familiar, Earth. Drop an apple, it falls. Why? Not because an invisible force pulls it, but because space-time itself is bent and the apple's future points downward. Here's the twist. Light is affected too. Imagine the apple emits tiny bubbles of light over time. Near Earth's surface, even these light rays curve downward under gravity's influence. Why? Because gravity curves time itself. Near a massive object, light cones tilt inward. The closer you get, the more pronounced the tilt. Eventually, the future itself points toward the center of the object. Now take this idea further. What happens when the mass becomes extreme? Let's look at black holes. Imagine person A lights a candle. The light spreads in all directions, forming a growing sphere of light, a light cone. Person B, standing at a distance, sees the candle only when the light reaches him, only when he enters that expanding light bubble. Once B is inside the light cone, he can't leave it unless he moves faster than light, which is impossible. Now imagine a star. It constantly emits light in all directions. Light bubbles that grow with time. But as the star collapses, it becomes so dense, so massive that its gravity pulls space inward at the speed of light. At a critical moment, the star emits one final bubble of light, a last desperate attempt to shine. But space itself contracts faster than the light can expand. That bubble becomes trapped. The light cone no longer opens outward. It freezes, collapsing inward. From that point forward, no light, nothing can escape. A black hole is a frozen bubble of light, locked in place by gravity. If we take a two-dimensional cross-section of space, a black hole appears as a stationary circle, but in space-time, that circle becomes a cylinder, extending from past to future. The boundary of a black hole is known as the event horizon. Above the horizon, light can still escape, but once you pass below it, not even light can get out. Inside, the light cones, those indicators of possible motion, tilt so steeply inward that every possible future leads to the center. In a very real sense, time itself points toward the singularity. To understand what a black hole truly is, we must consider 2 points of view, that of a distant observer watching from afar, that of an astronaut falling into the black hole. From the perspective of a distant observer, gravity is weak and space-time appears flat. Time flows in a straight line, left to right on a diagram. The event horizon seems fixed, represented as a line stretching from past to future. The black hole looks motionless and eternal. But for the falling astronaut, things look very different. As they approach the event horizon, space and time distort more and more. At the moment the astronaut reaches the horizon, they don't feel anything unusual, no bump, no jolt. But something profound happens. Space and time are now tilted at a 45 degrees angle. For the astronaut, the event horizon is no longer a horizontal boundary. It becomes a diagonal surface, just like the edge of a light cone, a surface beyond which escape is impossible. While the distant observer sees the black hole as a stationary object, the astronaut sees it as a light trap. Once they cross the event horizon, space and time switch roles. What used to be space, directions you could move, becomes time, a one-way path forward. What used to be time becomes part of the spatial geometry. Inside the horizon, the center of the black hole is no longer a place, but an event in the future. The horizon itself is no longer a location. It's now an event in the past. When a massive star collapses under its own gravity, it emits a final burst of light, a last, desperate bubble of photons trying to escape. But space-time is now so warped that even this bubble freezes, unable to expand. This marks the formation of a black hole, a region of space-time that behaves like a stationary light cone, forever sealed by gravity. If we straighten the diagram, time flows again from left to right. The event horizon becomes a cone of no return, a surface from which no signal can escape. Once we cross it, we are inevitably pulled inward, toward a singularity where our current physical models break down. In Penrose diagrams, this entire scenario is compacted and visualized. The outer universe and the interior of the black hole are clearly separated. Crossing the event horizon means leaving the observable universe forever. From that moment on, every future path leads only to the singularity. All right, we've traced how light cones behave inside a black hole, but what about the edge of a black hole? What's it like just outside the event horizon? Let's go back to Miller's Planet from the film Interstellar. Yes, the science in the movie was supervised by Nobel laureate Kip Thorne, so let's take it seriously. Miller's planet orbits Gargantua, a supermassive black hole. In the movie, just 5 minutes on the planet equals years on Earth. This isn't fiction. It's a direct consequence of Einstein's relativity. Time slows down in a strong gravitational field. The closer you are to a massive object, the slower time flows for you compared to someone farther away. But gravity isn't the only thing that warps time. According to special relativity, time also slows down for fast-moving objects. Here's a simple example. Imagine climbing a staircase. You're gaining height, so you're moving away from Earth's gravitational pull. That should make time tick slightly faster for you. But you're also in motion, and motion slows time down. Surprisingly, these two effects cancel each other out. Let's consider two people. Person A is floating near a massive object like a planet or a star. Person B is drifting far away, in the emptiness of space, where gravity is negligible. Person A shines a green laser toward Person B. A laser beam is a wave of light, in this case, vibrating 600 trillion times per second. But light is also a form of energy. As that beam climbs out of the gravitational field, it loses energy. Its frequency drops. By the time it reaches Person B, it no longer vibrates at 600 trillion times per second. Maybe it's only vibrating 10 billion times per second now. The green light has redshifted, stretched into microwave radiation. This is a real and measurable phenomenon called gravitational redshift. But where did the rest of the vibrations go? They didn't just disappear. Person A still emits 600 trillion vibrations per second, while Person B receives only 10 billion per second. The only explanation is this: a second for one person is not equal to a second for the other. Person A needs only 1 second to generate those vibrations, but for Person B, receiving them takes 60,000 seconds, nearly a whole day. Their clocks are running at different speeds, and it's not just mechanical clocks. It applies to biological ones too. The heart, the lungs, the brain. Person A breathes in, breathes out. Everything feels normal, but from Person B's perspective, watching through a telescope, everything happens in extreme slow motion. Days pass between breaths. Now let's return to Interstellar. According to the theory of relativity, the stronger the gravitational field or acceleration, the slower time flows. On Earth, gravity is modest. Time slows down by only a few microseconds per day. But on the surface of a neutron star, gravity is enormous, and time slows by several hours per day. And at the event horizon of a black hole, time stops altogether. Gravity is so intense that not even light can escape. On Miller's planet, which orbits the black hole Gargantua, time flows much more slowly than on Earth. That's because Gargantua's gravity is 1 billion times stronger than the Sun's. In the movie, when the crew steps onto the planet, a ticking sound begins, 1 tick per second. But each of those seconds equals 1 Earth day. That's 61,400 Earth seconds for every second on Miller's surface. Time doesn't just slow, it nearly halts. In reality, time flows differently everywhere in the universe. Take the International Space Station. Time on the ISS passes slightly more slowly than on Earth. The difference is tiny, but measurable. That's why we adjust GPS satellite clocks with Einstein's equations. Otherwise, they'd quickly drift out of sync. But gravity isn't the only way to slow time. The second way is speed. The faster you move through space, the slower you move through time. Let's say you board a spaceship headed for the Andromeda Galaxy, 2.5 million light-years away. If your ship travels close to the speed of light, the round trip might take only 18 years from your perspective. But on Earth, 5 million years would pass. This is not fantasy. It's what relativity predicts. So what connects acceleration and gravity? Let's look up at the sky. Somewhere up there, astronauts are floating aboard the International Space Station. A screwdriver released from their hands simply hangs nearby. Drops of water drift around like trembling bubbles. Why? They haven't left Earth's gravitational field. The station orbits only about 400 kilometers above the surface, roughly 10 times higher than a passenger jet. The station is falling toward Earth, just like you would if you jumped from a plane, but it's moving forward so fast that it constantly misses the planet. That's what we call free fall. And the key idea here is that free fall is indistinguishable from floating in deep space. If you were inside a sealed spaceship with no windows, you wouldn't be able to tell whether you were far from any gravitational field or simply falling freely inside one. everything around you would float, not because there's no gravity, but because gravity acts equally on all parts of your body. There's no force pushing you in any direction. Einstein called this the happiest thought of my life. A person in free fall feels no gravity. In other words, gravity can be simulated by falling. Conversely, the effects of gravity can be created by acceleration. If you start accelerating in your ship with the same force as Earth's gravity, you'll feel perfectly normal. You could sit in a chair, walk around the cabin, everything would feel just like being on Earth. And if you reduce the thrust to a third, you could imagine you were on the surface of Mars. Here's the truly remarkable part. No other force in nature behaves this way. The force between two electric charges can't be mimicked by acceleration, but gravity can. This is the essence of the equivalence principle. Einstein's great insight that acceleration and gravity are locally indistinguishable. It opened the door to a new understanding of reality, one that leads us straight to black holes and the most extreme geometries in the universe. In 1916, just 5 months before his death, German astrophysicist Karl Schwarzschild made a historic discovery. He was serving in the army at the time, calculating artillery trajectories, when he found the first exact solution to Einstein's newly published equations of general relativity. Einstein had released his theory only weeks earlier. Schwarzschild quickly derived his solution and sent it to him. Einstein was astonished. "I read your paper with great interest. I never expected an exact solution to be so simple." Schwarzschild described the curvature of space-time around a spherical mass, like a star. Remember John Wheeler's famous quote? "Space-time tells matter how to move. Matter tells space-time how to curve." Well, Schwarzschild's solution gives us the math for that curvature. Let's bring it back to Earth. Our planet's surface is curved. You can't use the Pythagorean theorem to calculate the distance between Buenos Aires and Shanghai. If you tried laying a giant 19,600-kilometer ruler from one to the other, the end wouldn't reach Shanghai. It would end up in space. The ruler is straight, but Earth is not. To measure distance properly, you'd need to lay out 20 million 1-meter rulers, one after another, following the curvature of the Earth's surface. A beautiful real-world example is the Montreal biosphere. From a distance, it looks like a perfect sphere, but up close, you'll see it's made of flat triangular panels stitched together at small angles. You can build any shape this way. In general relativity, space-time is constructed the same way, from countless small, flat regions stitched together. Schwarzschild's solution tells us how they're connected around a massive object. Einstein's happiest thought comes back again. If a falling observer feels no gravity, then space-time must be flat in their local frame. Gravity doesn't arise from some invisible force pulling on things. It's the result of tilted pieces of space-time, sections that are slightly angled relative to their neighbors in the presence of mass. For the Sun, this curvature is mild. On its surface, time slows down only slightly. Clocks lag by about 1 minute per year. But when it comes to black holes, the distortion becomes dramatic. Here's the astonishing part. Schwarzschild's solution doesn't just describe space around a star. It also describes a black hole. You just keep adding mass, and when the star becomes compact enough, the equations still hold. This model, known as the Schwarzschild black hole, is the simplest possible black hole. It doesn't rotate, and it has no electric charge. It's defined by a single parameter, mass. The boundary of this black hole, the event horizon, has a radius given by a simple formula, the Schwarzschild radius. But physicists soon began to wonder, do such perfect, static, symmetrical black holes actually exist in the universe? In reality, most massive objects spin. They're not perfectly spherical, they bulge slightly at the equator. It took over 50 years before scientists found a solution to describe a rotating black hole. Now let's return to Penrose diagrams. These clever illustrations compress infinity onto a page, letting us visualize entire universes and black holes in a finite space. Each edge or vertex of a Penrose diagram represents some kind of infinity, infinite space, infinite time, or the unreachable singularity. But here's the mystery. Look at the Penrose diagram for an eternal Schwarzschild black hole. The left edge isn't at infinity. It sits at a specific coordinate. R equals 1, the Schwarzschild radius, the event horizon. So far, we've only talked about the upper half of that edge, the one we cross when we fall into a black hole. But what about the lower half? Nothing can cross this edge from inside the diagram, but since it doesn't represent an infinity, perhaps something is hidden behind it? In 1935, Albert Einstein and Einstein-Rosen were the first to realize that there might truly be something behind the event horizon of a black hole. As they studied the mathematics of the Schwarzschild solution, they realized they had been looking at only half of the full picture. The complete solution, it turned out, was far stranger than anyone had imagined. They wrote, "Four-dimensional space is mathematically described by two sheets connected by a hyperplane. We call this connection between two sheets a bridge." What they discovered was that a Schwarzschild black hole isn't just a one-safe funnel into destruction, it's a bridge between two universes. Einstein called it a bridge between two worlds. Today, we call it a wormhole. It turns out that when we draw the standard Schwarzschild diagram, we're only seeing half the solution. The full Penrose diagram contains not just two, but four distinct regions. Region 1, our familiar universe, outside the black hole. Region 2, the interior of the black hole, where space and time are so distorted that all paths lead to the singularity. Region 3, another entire infinite universe completely disconnected from ours, except inside the black hole. Region 4, a hypothetical object known as a white hole, the mirror image of a black hole. Everything flies out of it, but nothing can fall in. The white hole exists in the past, not the future. In that sense, it resembles the Big Bang, a singular event that explodes outward, giving rise to a universe. A black hole lies in the future for astronauts from two infinite universes, and they can decide whether to jump into it or not. A white hole, on the other hand, lies in the past for them. They can receive signals from it, but they will never be able to visit it. This is where things get really strange. The two universes, ours and the parallel one, are connected through a wormhole inside the black hole. An astronaut from our universe can enter the black hole. An astronaut from the other universe can do the same from their side, and inside, just before the singularity destroys them, they could actually meet. According to the diagram, an astronaut from Region 1 can cross into Region 2, the black hole's interior, and encounter another astronaut who entered from Region 3, the parallel universe. For a brief moment, they can even communicate. Then, both will be pulled into the singularity, where time ends. This extended picture is known as the maximally extended Schwarzschild space-time. The word maximally has a technical meaning here. It means that all possible world lines, the paths of objects through space and time, are included. In this version of space-time, those world lines either continue forever or they end at the singularity. The astronauts we have been considering in their journeys around and into the black hole are immortal. Their world lines must be infinitely long unless they encounter the singularity. In other words, their lives are infinite unless they cross the event horizon. But there's a catch. Even though the diagram suggests a bridge, no one can actually cross the wormhole. The reason is that time inside a black hole behaves differently. The spatial coordinate becomes time-like, meaning that falling inward becomes as inevitable as aging. Everything is pulled inexorably toward the center, and the wormhole itself changes over time. It stretches and collapses faster than anything can travel through it. Even light can't keep up. The wormhole closes before anything can cross. This leads to an obvious question: do such exotic objects exist in reality? The answer is likely no, at least not in this form. Eternal, symmetrical Schwarzschild black holes probably don't exist. Real black holes form from collapsing stars, and those are dynamic, messy, rotating, and asymmetric. The idealized black hole of Einstein and Schwarzschild may never arise naturally. But here's the fascinating part. Einstein's equations do allow for the existence of wormholes. In 1988, physicist Kip Thorne and his colleagues began exploring one of the most audacious ideas in physics. Could wormholes be stabilized? They asked a provocative question. Do the laws of physics allow a highly advanced civilization to build and maintain wormholes for interstellar travel? Such wormholes wouldn't be formed by collapsing stars. Instead, they might be extracted from quantum foam, enlarged to a classical size, and stabilized using quantum fields with negative energy density. In theory, such an object could serve as a portal through space or time. But that introduces disturbing implications. Could an advanced being measure Schrödinger's cat as alive, then travel back in time through the wormhole and kill the cat, changing the outcome? Today, scientists are still fascinated by wormholes. Some even propose that they may be part of spacetime's fundamental structure, woven into the quantum fabric of the universe. We'll return to that idea later. In 1963, mathematician Roy Kerr made a breakthrough. He discovered the exact solution to Einstein's equations for a rotating black hole. You might think that adding rotation to Schwarzschild's 1916 solution would be a small step, but the fact that it took nearly half a century tells you just how difficult the problem really was. Kerr's solution, like Schwarzschild, describes an eternal black hole, a stable vortex in empty space. But unlike Schwarzschild's black hole, which is perfectly spherical and static, Kerr's black hole rotates, just like real astrophysical objects, stars, planets, and galaxies. That loss of symmetry has profound consequences. A slowly rotating Kerr black hole differs from a Schwarzschild black hole in three major ways. First, the singularity is no longer a point, it's a ring. The plane of that ring lies perpendicular to the black hole's axis of rotation. Only trajectories that fall exactly into the equatorial plane will collide with the singularity. All other paths pass by. In theory, an astronaut could fall into a Kerr black hole and not die. They could avoid the singularity entirely. Second, a Kerr black hole has not one but two event horizons, an outer and an inner. Third, there is a region outside the outer horizon where space is so twisted by rotation that nothing can remain stationary. This region is called the ergosphere. Imagine you're an astronaut approaching a Kerr black hole. The first thing you encounter is the ergosphere, a violently twisted region of space-time. You can't hover here. Even if you fire your engines full blast, you'll still be dragged along with the rotation, like being caught in a whirlpool. Even light can't hold still. It spirals inward. But there's hope. The ergosphere is not a point of no return. You could in principle escape by using the black hole's own rotation to slingshot yourself outward, like a surfer riding a gravitational wave. Let's say you continue anyway. You cross the outer event horizon. Now, escape is impossible. You fall inward until you cross the inner horizon. And this is where things get bizarre. Inside the inner horizon, you regain your freedom. The singularity is no longer in your future. Time doesn't have to end. You can fly inside the black hole, avoiding the ring singularity entirely. To ensure that all world lines end either at infinity or at the singularity, we are forced to expand the diagram. The result is quite shocking. Inside a Kerr black hole is a structure so strange it defies belief. An infinite number of infinite universes, nested inside each other like Russian nesting dolls. A Penrose diagram couldn't capture it. You'd need an infinite sheet of paper. This Kerr wonderland contains an endless tower of alternate universes, with new regions opening up as you pass through the inner horizon. There is no inevitable encounter with a singularity. Time doesn't have to stop. You may ask, what on earth is happening here? But this is what the math demands. In theory, you could cross the inner horizon, loop around the ring singularity, exit through a white hole horizon into a new universe, find another black hole in that universe, dive into it, and repeat the process endlessly. If you decide to fly through the ring singularity, you might end up in an anti-gravity universe, where gravity repels instead of attracts. What's more, closed time-like curves, loops in space-time, may exist here. Such paths cannot be depicted on a Penrose diagram because they require a detour in one of the unshown dimensions. These trajectories are called closed time-like curves. Imagine a path in space-time that starts the day before you were born and, after a few years, according to your clock, returns to the same day. That's time travel. Such paths are allowed by the geometry of space-time. This means that Kerr's black hole is a time machine. All sorts of questions arise. What if you decided to prevent your own birth? This is not necessarily a paradox. The universe may be structured in such a way that time travel is possible, and yet everything remains logically consistent. Stephen Hawking once proposed the chronology protection conjecture, the idea that the laws of physics must somehow forbid time travel. It was his way of defending the universe from paradoxes, grandfather conundrums, and closed time-like curves. Time travel, he believed, should be blocked by some fundamental principle. Most physicists agree that Kerr's maximally extended geometry, with its infinite nesting of universes and built-in time machines, likely does not exist in nature. Real black holes formed from the collapse of stars. Collapsing matter alters the internal geometry, cutting off wormhole-like passages to other universes. Furthermore, any infalling matter or radiation would create an infinite energy buildup along the inner horizon, generating a singularity that seals the exit. But it gets even stranger. If a Kerr black hole spins too fast, beyond a certain critical limit, the event horizons disappear. What's left is a naked singularity, a ring-shaped singularity fully exposed, with no protective horizon. And to physicists, that's a nightmare. A naked singularity is a breakdown of space-time, left visible to the universe. There's no event horizon to shield us from its chaos. It's like a glitch in the fabric of reality, a place where the laws of physics stop working and we can see it happen. Roger Penrose was so disturbed by the idea that he proposed the cosmic censorship conjecture, which asserts there are no naked singularities in nature, except perhaps for the Big Bang itself. Why is this such a big deal? Because naked singularities destroy determinism. If information can leak out of a singularity, then the future becomes unknowable, even if we have complete knowledge of the past. Cause and effect fall apart. In 1991, Kip Thorne, John Preskill, and Stephen Hawking debated whether the laws of physics truly forbid naked singularities. Hawking argued that they did under all circumstances. Thorne and Preskill weren't so sure. Then in 1997, Hawking lost the bet. Computer simulations showed that under certain conditions, naked singularities can form, even without invoking exotic physics. The simulations were admittedly extreme, but they were still consistent with general relativity. Hawking conceded defeat. The story made the front page of the New York Times. The caveat, he admitted, is that the simulations are highly contrived, but they don't require anything outside known physics. The three physicists made a new bet. This time they rephrased it. No naked singularity will ever form naturally unless an unimaginably advanced civilization somehow intervenes and fine-tunes the collapse of matter. Hawking paid up by giving Thorne and Preskill t-shirts that read, "To cover the nakedness of the winners." But what prevents a Kerr black hole from spinning too fast and exposing its singularity? It sounds easy to imagine. Just throw a fast-spinning star into it. Make sure the spin aligns with the black hole's rotation. This will increase its angular momentum. The math is simple. General relativity allows you to calculate the effect. But something surprising happens. The black hole repels the star. Such a spin-spin interaction clearly shows that general relativity is designed to ensure that cosmic censorship is observed, physicists noted. In natural black holes, singularities are always hidden behind the horizon. This may seem like the universe playing defense, like reality itself refuses to let us see its most vulnerable points. If you're disappointed that nature seems to disallow wormholes and time machines, don't be. If you're upset that nature does not seem to allow the existence of wormholes and Kerr black holes, you're probably too pessimistic. Kip Thorne once said, "The main thing is that general relativity is rich and allows for an amazing diversity of spacetimes. Perhaps some of this exoticism is realized in nature." Rotating black holes are not exotic. They exist, and the space-time around them is described by Kerr's solution. Roger Penrose realized that energy can be extracted from a rotating black hole. This is done as follows. Throw an object into the ergosphere. Make sure that it breaks into two parts. One part should fall into the hole and the other should fly out. If everything is calculated correctly, the part that flies out will carry more energy than the entire original object. But how is this possible? The secret is that objects with negative energy are possible inside the ergosphere. This is a consequence of the reversal of the roles of space and time. Physicist Emmy Noether made one of the most profound discoveries in modern science. Every conservation law corresponds to a symmetry in nature. The conservation of energy stems from the symmetry of time, the idea that the laws of physics don't change from one moment to the next. The conservation of momentum arises from the symmetry of space, that physics works the same here as it does elsewhere. But what happens when space and time swap roles as they do near a rotating black hole? Surprisingly, energy can become negative. This leads to an astonishing possibility. If an object with negative energy falls into a black hole, the black hole's total energy, and therefore its mass, will decrease. But energy must still be conserved. That means the other piece of the object, the one not swallowed, can fly back out with more energy than was originally input. This is known as the Penrose process, and it offers a potential method to extract energy from a rotating black hole. An advanced civilization could, in theory, use this process to dispose of waste and generate electricity, a cosmic-scale source of green energy. But there's a limit. Although the black hole loses energy and slows its rotation, its event horizon always grows in area. This is not a guess, it's a theorem. In 1971, Stephen Hawking proved that, regardless of what happens, the surface area of a black hole's event horizon can never decrease. This is the foundation of black hole thermodynamics. In my entire scientific career, spanning 45 years, the most amazing experience has been the realization that the exact solution to Einstein's equations, discovered by Roy Kerr, gives an absolutely accurate representation of the countless massive black holes that inhabit the universe. This awe of beauty, this incredible fact that a discovery born of the search for beauty in mathematics finds its exact reflection in nature, convinces me to say, beauty is what the human mind responds to in the deepest and most intimate way. The elegance of black holes lies not only in their mysterious behavior, but in their astonishing simplicity. Black holes are the most perfect macroscopic objects in the universe, and since general relativity provides a single family of solutions to describe them, they are also the simplest. The Schwarzschild solution, found in 1916, describes a non-rotating black hole using only one number, mass. The Kerr solution, found in 1963, adds just one more number, spin. Together, these two parameters are enough to fully describe the gravitational landscape outside any real black hole. It doesn't matter what collapsed to form the black hole, a star, a planet, or even a pile of old encyclopedias. Once the event horizon forms, all the complexity vanishes. Only mass and spin remain. The solutions to Einstein's equations, found by Schwarzschild and Kerr, are of enormous importance because they are the only ones possible for spacetime outside any black hole. Nowhere else in physics does something as complex as a collapsing star boil down to something so simple and precise. This is what inspired Subrahmanyan Chandrasekhar, the Nobel laureate who dedicated much of his career to the study of stellar evolution and black holes. And John Wheeler summed it all up with legendary brevity. Black holes have no hair. In his memoirs, Wheeler joked that Richard Feynman accused him of using indecent language in a physics lecture. I was just trying to summarize the remarkable simplicity of a black hole by saying that a black hole has no hair. I was thinking of a room full of bald people who are difficult to distinguish. No differences in length, style, or color. That's what a black hole is like. And yet, there's something melancholic in how nature reveals its deepest beauty. The real treasures seem forever hidden from us. Black holes have horizons, boundaries beyond which information vanishes from our view. They seem to condemn us to eternal blindness about the details of what falls into the singularity. In fact, it is precisely this blindness that makes the Schwarzschild and Kerr solution so useful. Black holes are not so black. This short phrase by Stephen Hawking would go on to change physics forever. Until 1972, black holes were thought to be simple. Matter falls in, the black hole grows, and nothing ever escapes. According to general relativity, all information about the matter is lost forever. But this raised a disturbing problem. Physicist John Wheeler once joked to his student Jacob Bekenstein that he felt like a criminal. He described putting a hot cup of tea next to a cold one and waiting until they reached the same temperature. The total energy stays the same, but the disorder of the system increases. That crime, Wheeler said, echoes to the end of time. He was talking about the second law of thermodynamics, the rule that the entropy of the universe always increases. Entropy is a measure of disorder. As things change, the universe becomes more chaotic. But what if a black hole floats by, Wheeler asked, and I throw both cups of tea into it? Doesn't that erase all evidence of my crime? The concern was serious. Wheeler imagined that he could reverse the entropy increase simply by tossing the evidence into a black hole. His student Bekenstein took this thought experiment seriously and went off to think about it. Months later, he returned with a groundbreaking idea. Black holes don't hide crimes, they record them. Hawking had previously shown that the area of a black hole's event horizon never decreases, a law that Bekenstein realized was mathematically similar to the second law. He proposed that the surface area of a black hole's horizon was a measure of its entropy. When something falls into a black hole, the area increases, and so does the entropy. The record is preserved. The second law is saved. But this raises a profound question. What is the entropy of a black hole? According to general relativity, black holes are extremely simple. A Schwarzschild black hole has only one defining feature, its mass. There are no internal parts, no distinguishable components. So where does the entropy, the hidden information, come from? To answer that, let's go back to the 19th century, when the foundations of thermodynamics were being laid not by theoretical physicists, but by practical inventors. One of them was James Joule, a brewer from Salford. In the 1840s, he built a clever experiment involving falling weights that turned paddles in a container of water. The paddles stirred the water, which warmed up. Joule showed that mechanical work could be converted into heat, that these were simply two forms of energy. This was the birth of the first law of thermodynamics. Energy cannot be created or destroyed, only transformed. Burn coal, boil water, spin a wheel. It's all energy, just changing forms. But that's not the full story of how a steam engine works. We're missing a crucial ingredient, the environment. A steam engine only works because the furnace is hotter than its surroundings. Heat flows from hot to cold, never the reverse. This is the second law of thermodynamics, and it governs everything from power plants to refrigerators. Your fridge doesn't create cold. It pumps heat from the inside to the outside. That's why the coils on the back of your fridge get hot. They're dumping the excess energy into your kitchen. The connection between entropy and disorder was first grasped by James Clerk Maxwell, who wrote, "The second law of thermodynamics has the same degree of truth as the statement, if you throw a glass of water into the sea, you cannot get the same glass of water back." Ludwig Boltzmann refined this idea and gave it mathematical form. According to his famous formula, entropy measures our ignorance about the exact microscopic configuration of a system. Take a pot of water, for instance. Before you pour it out, you know that all the water molecules are in the pot. After pouring it, you have almost no idea where the individual molecules ended up. The system's entropy or uncertainty has increased. Put simply, entropy is a measure of what we don't know. This concept found an unexpected connection with information theory in the 20th century, thanks to Claude Shannon. He showed that entropy and information are closely linked. Here's a simple illustration. Suppose you flip a coin. It has two possible outcomes, heads or tails. Let's label them 0 and 1. That gives you one bit of information. If you flip two coins, you now have 4 possible outcomes, requiring 2 bits to describe. 3 coins, 8 outcomes. 3 bits? The rule is that the number of bits needed to describe a system is where W is the number of possible configurations. Wait a minute, doesn't that look familiar? Yes, it's strikingly similar to Boltzmann's formula for entropy. What Shannon showed is that entropy and information are 2 sides of the same coin. Entropy tells us how much information is hidden within a system, how many microscopic arrangements could correspond to what we observe on the outside. And if we take Bekenstein's insight seriously, that the entropy of a black hole is proportional to the area of its event horizon, then entropy becomes a window into the structure of space and time itself. But there's a paradox. Black holes, as described by general relativity, have no constituent parts. They are smooth, featureless, geometric objects made entirely of warped space-time. So how can they store information? On the surface, you'd think a black hole should have 0 entropy. Throw a couple of teacups into one and its mass increases. But that's it. No complexity is visible. That was the traditional view. But Bekenstein disagreed. To preserve the second law of thermodynamics, he proposed that black holes do have entropy and that it must be proportional to the area of the event horizon. He went further and tried to calculate this entropy. Suppose you wanted to send just 1 bit of information into a black hole. You could simply fire in a single photon polarized either clockwise or counterclockwise. That gives you 2 options. 1 bit. Bekenstein showed that the total number of bits a black hole can store is equal to the area of its event horizon, measured in Planck units. Let's pause here. The Planck length is the smallest length scale in the universe, about 10 to the minus 35th power meters. For comparison, it's roughly a billion trillion times smaller than a proton. If you tile the black hole's horizon with squares the size of the Planck length, let's call them pixels. Each pixel holds 1 bit of information. This is a mind-blowing result. According to Einstein's general relativity, the event horizon is empty, just a boundary in space. An astronaut falling through it wouldn't feel anything unusual. But Bekenstein's logic suggests that the horizon is actually a dense shell of encoded bits, each one silently storing information about what has fallen in. In other words, the entropy of a black hole equals the number of bits it hides. We can calculate it by laying out the event horizon in Planck scale pixels, assuming 1 bit per pixel. It's hard to overstate how radical this idea is. It raises profound questions. What are these Planck pixels really made of? Why do they exist only on the horizon, not inside? Why is a black hole's information capacity proportional to its area, not its volume? How much information can be stored in a library? Obviously, the answer depends on the number of books that can fit inside. However, for a black hole library, it seems that we can only cover its outer walls with pages, as if the interior space does not exist. A black hole has the maximum possible entropy. It can store the maximum amount of information in a given volume of space, and the amount of information in bits is determined by the area of the region in Planck units. This suggests something deeply hidden. Everything that exists in volume can be completely described by the information on the surface surrounding it. This is our first encounter with the holographic principle. History repeats itself. When Boltzmann died in 1906, his explanation of entropy through atoms was not accepted. Scientists doubted the existence of atoms. They did not like the statistical nature of the second law. Today, similar debates are taking place about black holes. If the entropy of a black hole means the presence of some moving parts, analogous to moving atoms, then general relativity is an approximate theory, and space-time is an approximate picture of reality. Space-time should be viewed as an approximation, an average description of the world, similar to the description of gas in a vessel using temperature, volume, and pressure. Perhaps we, the people of the 21st century, are simply incapable of perceiving the true structure of space-time. When Bekenstein made his assumption that black holes have entropy, there was one huge problem. Entropy and temperature go hand in hand. If a black hole has entropy, it must also have temperature. And to have temperature, an object must emit, not just absorb. But everyone knew that nothing can escape from a black hole. But in 1974, everything changed. Stephen Hawking published his famous article, "Black Holes Turned Out to Be Not So Black After All. They Glow Softly, Like Dim Coals, Very Dim Coals." The temperature of a black hole with the mass of the Sun is this many degrees above absolute zero. That is millions of times colder than the universe. Stephen Hawking's article sparked a revolution in theoretical physics that continues to this day. He discovered that quantum theory predicts the radiation of a black hole as if it were a normal object with a certain temperature. The immediate conclusion is that the law of gravity should be viewed as a statistical law, and quantum effects generate elementary randomness in the geometry of space. Today we do not know what exactly this randomness corresponds to. It remains the holy grail of theoretical physics. In 1973, Barden, Carter, and Hawking discovered a surprising connection between the laws of thermodynamics and the properties of black holes. Temperature can be replaced by surface gravity, and entropy can be replaced by area. The similarity is striking. At first they thought it was just an analogy. Black holes seem to be objects with a temperature of absolute zero. After all, nothing can escape from them. But a year later, Hawking changed his mind, stating that black holes create and emit particles. But how is it possible for an object from which nothing should escape to glow like coal? The answer lies in quantum theory and vacuum physics. Quantum mechanics differs from classical physics. It describes a world of probabilities. Heisenberg's uncertainty principle states that it is impossible to know both the position and velocity of a particle at the same time. This is not our ignorance, this is how nature works. The vacuum of empty space is not empty. Quantum theory does not allow for absolute emptiness. Any particles can be thought of as excitations of the vacuum, like ripples in a vacuum sea. Particles are constantly being born and disappearing in a vacuum. These ghosts are vacuum fluctuations. Scientists call them virtual particles. If we could freeze time and look deep into any area of space with high resolution, we would see these particles not as fleeting ghosts, but as real, actual particles. And this is exactly what happens to time and space near the horizon of a black hole. A black hole acts like a magnifying glass, freezing time. Virtual particles appear from the vacuum in pairs. One has positive energy, the other negative. Usually they quickly reunite, but something special happens at the black hole's horizon. Hawking explained how black holes emit radiation. Virtual particles at the horizon can split apart. The particle with negative energy falls into the hole, reducing its mass, and its partner flies off into the universe as Hawking radiation. The temperature of a black hole is inversely proportional to its mass. Small black holes are hot, large holes are cold. Hawking's formula combines quantum theory and general relativity. It proves that the laws of black hole mechanics are disguised laws of thermodynamics. This formula is now engraved on Hawking's tombstone. Black holes are not really that black. They glow with quantum light, combining thermodynamics, quantum mechanics, and gravity into a single picture. Hawking radiation has three properties that together seem confusing. 1. If you are falling freely near the horizon of a large black hole, you will not encounter any radiation. 2. If you accelerate to hover above the event horizon of a large black hole, you will be vaporized by a stream of red-hot radiation. 3. If you are far away from a black hole, you will feel a stream of cool radiation. These three descriptions seem contradictory. Imagine you jump into a black hole. From your point of view, you calmly cross the horizon, but your friend outside will not see this. Instead, they will see you burn up. Let's say you jump into a large black hole. From your perspective, you will inevitably be spaghettified as you approach the singularity, but you will cross the event horizon without any drama. Your friend in the ship outside the hole will never see you cross the horizon, but will watch you get closer and closer. We know this from general relativity. Your friend can lower a thermometer to you to measure the temperature at your point near the horizon. The thermometer, hovering above the horizon, will experience vacuum fluctuations and find itself immersed in a hot bath of radiation. From this position, the area near the horizon is a hot spot. Your friend might conclude that you were charred outside the black hole and never crossed the horizon. Should we abandon the principle of equivalence, the very foundation of general relativity, and admit that the horizon is dangerous and hot? Or should we insist that a freely falling observer passes through the horizon without incident and conclude that something is wrong with our quantum calculations of the vacuum? By choosing either of these positions, we are forced to discard the core of either general relativity or quantum theory. It sounds completely absurd. How can you simultaneously cross the horizon and evaporate? Physicists searched hard for an explanation and eventually found one. There is a way out of this paradox: the complementarity of black holes. In fact, both descriptions are correct. From the outside, a black hole has a hot, impenetrable atmosphere that vaporizes everything, including you. But if you look from inside a black hole, the horizon is nothing. You can pass through it without any problems. It turns out that a person can be both spaghettified and vaporized at the same time. From the outside, no one ever sees anything fall into a black hole. You could say that its interior lies beyond the end of time for an outside observer. Everything enters the hot atmosphere and burns up. To an outside observer, a black hole is little different from a hot coal. From the point of view of the complementarity paradigm, this does not contradict the story of the faller. He explores the interior and encounters the singularity. But, and this is the key point, he cannot communicate this to the outside world after crossing the horizon. Equally important is that outside observers are unable to inform the faller that he is burned up. Contradictions are avoided because the parties will never compare their records. Once again, there is no contradiction because observers will never be able to compare their records. You, falling into the hole, will not be able to communicate to the outside world that you are alive. At the same time, your friend on the outside will not be able to communicate to you inside that he saw you burn up. You may immediately object. What if the outside observer collects the ashes of the falling person and then jumps in after them and shows their friend that they were burned? Meeting one's own ashes would be unpleasant, even for a supporter of complementarity. The solution, according to complementarity, is that gathering evidence takes time. By the time the outside observer collects the ashes and crosses the horizon, his friend has already been spaghettified and cannot see the evidence of his own demise. Oddly enough, this seems to be the correct picture. The title of Hawking's first article was the question, "Do black holes explode?" Its essence is that the temperature rises as the hole shrinks. It emits more and more energy, then collapses and disappears in a flash. This is a slow process. A typical black hole with the mass of the sun will live for 10 to the 69th power years. That's a very long time, but not forever. It may seem that we don't need to worry about black hole explosions. Where are we? And where are 10 to the 69th power years? But if we don't think about it, we would miss what is possibly the most important revolution in physics since Einstein. The revolution was triggered by the following question: do black holes destroy information? Imagine that you decided to throw the Bible into a black hole. After an unimaginable amount of time, the hole would evaporate. Only radiation would remain. According to Hawking's calculations, this radiation is thermal, which means there is no information at all. It turns out that the book would be erased from the universe. All information about everything that fell into the hole would disappear. Instead, all that remains is a bath of faceless thermal radiation. In his book, The Black Hole War, Leonard Susskind recounts how, in 1983, Stephen Hawking first claimed that black holes destroy information. Future Nobel laureate Gerard Hooft stared sullenly at the blackboard for a full hour after Hawking's presentation. I can still remember the deep wrinkle on Gerard's forehead and Stephen's mischievous smile. Hooft frowned, because the known laws of physics preserve information. Knowing the exact state of a system, we can predict its future and reconstruct its past. This is determinism, the fundamental idea that the universe evolves predictably. If black holes destroy information, determinism breaks down. In the distant future, it will be impossible to reconstruct details of the past. This problem is called the black hole information paradox. Once again, complementarity resolves this paradox. From an external perspective, nothing falls over the horizon. Think of the Bible. From an external observer's perspective, the book is burned on the horizon and its ashes are returned to the universe as Hawking radiation. It is no different from burning a book at the stake. If you burn a book, the information can be recovered if you make precise enough measurements of all the ashes, gases, and embers. In practice, this is almost impossible, but some superintelligence could do it. Because the information in a burning book is jumbled, not destroyed, it simply changes form from words on paper to particles in space. The information is not destroyed. It is merely transformed from letters on a page to particles in space. It is obvious that as the book burns to the point of crossing the horizon, world lines can be drawn, connecting every atom in the book to a future time-like or light-like infinity. Compare this with the view from inside a black hole. The book is spaghettified near the singularity. We don't know what happens at the singularity, but since it's beyond the horizon, the book can't get out. It is destroyed at the end of time inside the horizon. But this is acceptable because, to an outside observer, the information is preserved. The book's histories are imprinted in Hawking radiation and are in principle always accessible to future superbeings. If we accept complementarity, both views are correct. We are accustomed to thinking that objects can only be in one place at a time. Quantum theory destroys this picture for subatomic particles, and complementarity is an even more radical challenge to intuition. It asks us to accept two equally valid views of what happens to a large object like an astronaut. You are both spaghettified and evaporated at the same time. Complementarity says that what happens inside the horizon is just as real as what happens outside. The two descriptions are equivalent. The inside of a black hole is somehow the same as the outside. This idea has become known as the holographic principle. At first glance, it might seem that there is no need to be so radical. One might imagine that when something falls through the horizon, it is secretly copied. One copy continues to fall into the singularity to be spaghettified. The other burns up at the horizon and is encoded as Hawking radiation. But there is a serious flaw in this logic. The laws of quantum physics forbid it. The no-cloning theorem says that it is impossible to make an identical copy of an unknown quantum state. With cloning ruled out, we are left with only one explanation: holography. Spatiotemporal holography was first presented by Gerard 't Hooft in 1993. Leonard Susskind developed it a year later. Both of them emphasize that holography must be a universal feature of nature, not just black holes. A hologram in the everyday sense is an image that appears three-dimensional and seems to float in space. A three-dimensional object is constructed from information stored on a two-dimensional screen. If you have seen a hologram, you know that they can look damn realistic. You can walk around them and look at them from all angles, as if they were ordinary objects. A black hole contains the maximum amount of information for its size. Scientists have discovered that the amount of information is measured not by the volume of an object, but by its surface area. This means that if you take any region of space, then all the information inside it is recorded on the boundaries of this region. Gerard 't Hooft and Saskind realized that any region of space cannot contain more information than can fit on its surface. The most cited paper in high-energy physics in the world was written in 1997 by physicist Juan Maldacena. It has almost 18,000 citations. More than any other paper, it has changed the face of theoretical physics in the last 25 years. It provides the strongest evidence yet for the truth of the holographic principle. The universe Maldacena envisioned is not the one we live in, but that's okay. Physicists often build simplified models. The important thing is that Maldacena did not choose a world specifically to support holography. Holography itself arose from mathematics. Maldacena's work is best understood through a toy 2D universe. The space of this 2D universe is not flat, but hyperbolic. It looks like this. This is a Poincaré disk. This is a projection that the artist Escher liked to use. Like the Penrose diagram, the space in this projection is infinite, and to fit it, you have to distort the image. Here's an example. Escher's fish. All the same size, and they fill an infinite hyperbolic space, but the fish appear smaller at the edge of the disk because we compress space as we move away from the center. Now imagine that we add a third dimension to this two-dimensional picture, time. You get a stack of Poincaré disks, one on top of the other, like a cylinder or a tin can. Time flows from the bottom up. Physicists call this space-time anti-de Sitter, and here's where the fun begins. Maldacena proved that everything that happens inside this can be completely described by events on its surface. Imagine you're looking at a tin can, and somehow, by observing only its surface, you can know everything happening inside it. As strange as it sounds, this is the essence of one of the most powerful ideas in modern physics. On the boundary of a cylinder, we find a world of ordinary particles obeying quantum mechanics. There's no gravity here, just particles moving on a flat surface. But inside the cylinder is something entirely different. A three-dimensional world filled with space, time, and gravity. Black holes form and evaporate. Space-time curves. It's the full machinery of Einstein's general relativity. And yet, these two worlds, one without gravity and one with it, are exactly equivalent. That's what Juan Maldacena discovered. The behavior of particles on the boundary fully determines the physics inside. When energy appears on the surface, a black hole emerges in the interior. As the particles settle down, the black hole evaporates in the form of Hawking radiation. It's a stunning idea. Gravity may not be fundamental at all. Instead, it could be a holographic projection of simpler quantum events at the edge of space. Maldacena proved that a quantum theory without gravity describes the same physics as a gravitational theory inside a higher dimensional space. So what's real? Is the black hole an illusion created by boundary particles? Or are the boundary particles themselves just a tool to describe something deeper? Maldacena offered a simple but powerful answer. There is no need to ask which description is true, because both are equal and equivalent. This is the holographic principle. Two completely different views, both right. And here's the twist. It suggests that our entire universe might be a hologram, fully described by information on a distant boundary. It sounds impossible, yet the math and evidence support it. Remember the black hole paradox, where an astronaut is both stretched into spaghetti and evaporated at the same time? How can it be explained? One might ask which of these two descriptions is the real one. Does a black hole really exist, or is it just a hologram of boundary physics? Or, on the contrary, boundary physics is not real and only serves as a clever way to describe a black hole? The holographic principle provides the answer. There are two equivalent descriptions of the world, and therefore no contradiction arises. Everything true in one is also true in the other. A black hole forms and then evaporates, leaving behind a beam of Hawking particles. The whole thing can be thought of as a gas of particles, evolving according to the usual rules of quantum mechanics on the boundary without gravity. Since there is an exact one-to-one correspondence between the boundary theory and the inner one, the conservation of information in one entails its conservation in the other. The boundary theory is a pure quantum theory, which means that information is inevitably conserved in it. Therefore, it is also conserved in the gravitational processes inside matter, during the formation and evaporation of a black hole. This is what convinced Stephen Hawking to admit defeat in a bet with Thorne and John Preskill, and agree that information does indeed escape from the black holes of our universe. He was convinced by Maldacena's paper. Maldacena finally answered the question of whether information can escape from a black hole. It can, but how exactly? Let's imagine two universes connected by a black hole, joined at a wormhole. This bridge is only possible if the two universes are quantum entangled. Think of quantum entanglement like two magical gloves. Open one box and see a right glove, and instantly, even from light years away, you know the other box holds the left. Except in quantum mechanics, the gloves are both right and left until you look. Einstein called this spooky action at a distance. And it turns out, when entanglement vanishes, the wormhole collapses. Space literally disconnects. Entanglement builds bridges, even between different universes. In 2006, Ryu-Takayanagi discovered a stunning link. The entropy of entanglement is proportional to the area of the smallest surface that separates two regions. In short, the more entangled two areas are, the thicker the wormhole between them. Then, in 2010, Mark van Ramsdonk made a bold claim: entanglement creates space. By changing the degree of entanglement, you can stretch, connect, or tear apart space. This means Einstein's gravity, space curving around mass, emerges from quantum entanglement. Without it, there would be no space at all. Back to black holes. Maldacena showed information isn't lost, but until 2019, no one knew how it escaped. The breakthrough came with the idea of islands. According to new calculations, some of the black hole's interior actually lies outside the event horizon, a region called an island that shares information with the outside world. At first, a young black hole has no island, but as it ages, an island forms, and eventually all information leaks out, a paradox resolved, using only Einstein's gravity and quantum mechanics. Think of a black hole as a prison. Hawking radiation escapes while its entangled partners remain inside. Eventually, the partners and their counterparts reunite, canceling out entanglement. Information begins to leak out. The singularity is no longer a final stop. It might be a network of wormholes. Picture yourself falling into a black hole. You cross the horizon and encounter what? Not oblivion, but quantum tunnels that stretch outward. You're torn apart, but your information survives, encoded in the Hawking radiation. These discoveries reshape our view of reality. Space isn't fundamental. It emerges from entanglement. Black holes are not cosmic vaults, but quantum processors, returning information via hidden links between the inside and outside. The universe is far more tangled, fluid, and connected than we imagined. Physicist John Wheeler once wrote, "All things physical are informational, and the universe is participatory." He also said, "Everything is connected to everything else." And he was right. Entanglement not only tracks information out of black holes, it creates space. And space is surprisingly resilient. Information is redundantly encoded like a quantum safety net. To rip space apart, you'd need to sever billions of invisible quantum links. And there's more. Quantum computers, the most powerful machines ever imagined, use the very same entanglement to process information. Protecting fragile quantum data is hard, but in 2015, 4 scientists developed the HAPPY code, a quantum error-correcting network that mirrors the holographic principle. Like a QR code, it stores information redundantly, except it does so using entanglement, not copying. Here's what's wild. The geometry of this code matches the geometry of space-time in Einstein's theory. The connections between qubits form a curved space. Space is not a backdrop. It's a pattern of relationships. No points, no lines, just entangled qubits woven into an invisible web. This is the holographic universe. From quantum entanglement, we get space. From space, gravity. From gravity, time. From all of it, our reality. We now simulate black holes on quantum computers. 2 once separate fields, gravity and computation, have merged. We live inside a kind of quantum computer the size of the cosmos. Are we digital ghosts in someone's simulation? Probably not, but we may have found the real source code of the universe. Wheeler said it long ago, it from bit. Reality arises from yes-no answers to quantum questions. And now we are beginning to understand how. As Van Gogh wrote, "Remember the stars and the infinity above. Then life will seem almost magical." And indeed it is. The study of black holes has led us to the discovery of the holographic universe, strange, logical, and beautiful in its interconnectedness. We are on the threshold of new discoveries. This is a time when abstract theories become useful technologies, when the search for answers to eternal questions leads to a revolution in computing, when studying the infinity in the sky explains the reality beneath our feet.